Okay, that looks good. All right, so I guess we can get started. Bogdan, if you're ready. Yeah.
Yep.
Hi, and welcome everyone to our research seminar today. Today's guest is Bogdan Kulynych from EPFL's SPRING Lab, where he's working with Carmela Troncoso. And in his research, Bogdan studies the harmful effects of machine learning, algorithmic and optimization systems, and he's leveraging security and privacy techniques and principles to develop mitigations against these harmful effects. And today, Bogdan has a talk on disparate vulnerability to membership inference attacks. Okay, Bogdan, the stage is yours. Take it away.
Thanks, Philip. Thanks for the introduction and thanks for inviting me. So again, I'm going to be talking about disparate vulnerability to membership inference attacks, which is our paper that has recently appeared at PETS, Privacy Enhanced Technology Symposium. And this is joint work with Mohamed Yahini, Giovanni Cherubin, Michael Veal, and Carmela Troncoso. So I'm going to start with the basics. What is membership inference attacks, right? So membership inference attack is an attack against the privacy of the training data of a machine learning or a statistical model. Specifically, in a membership inference attack, the adversary is asking the question, was a given record that usually we're going to assume corresponds to some information about the individual. So was this given record part of the training data or not? And the adversary will need to answer this question by taking a look at the trained model in some way, maybe querying it, maybe looking under the hood, or something else. And these attacks are possible because machine learning models can sometimes be a bit like parrots. They memorize something from their training data, and then at test time, they will regurgitate it. And this will enable the adversary to tell what was in the training data from something that was not in the training data. If you're not familiar with membership inference attacks, they are real and they can be pretty effective. And prior literature on membership inference attacks has observed that different records can be differently vulnerable to these membership inference attacks. So some records can be more easy to identify as having been in the training data set as the others. And this observation comes in two flavors. To show it, let's imagine we have a plot like a histogram that shows for different records how vulnerable they are and the frequency of this vulnerability value. So in this plot, each point corresponds to one record, and the higher it is, the higher is the vulnerability. So in the first flavor of this observation, some researchers have seen that there are records that are not necessarily semantically connected in some way, that have higher vulnerability than most of the other records. So they are kind of outliers in the sense. And in the second flavor, other researchers have observed that there could be whole groups of records that have higher vulnerability than the others. And the difference in the second scenario from the first one is that in this group case, these outliers that have higher vulnerability, they are all semantically connected, right? So in this talk, I'm going to focus on the second flavor. They are similar, but they require different technical tools and formalizations to work with them. So why do you want to study this particular phenomenon? Why do you want to study disparate vulnerability to membership inference attacks across some population groups? Well, there can be different arguments that we can make, and I'm going to make in particular a legal argument. Since the adoption of GDPR and very similar data protection legislation around the world, if I remember correctly, similar data protection legislation has been introduced in more than 100 countries around the world. It has become hard to transfer personal data between companies, between organizations, and across borders. Right? Because, according to the data protection legislation, this has to be done carefully. So there has been incentives to the organizations that want to transfer the data or trade it to, instead of training the actual data, trading the actual data, to transfer the statistical machine learning models that are trained on this data. And the promise here is, if a statistical machine learning model is sufficiently anonymized, so if it's not any more personal data, then it should be easier to transfer it or to trade it than the actual data, which seems reasonable, right? But how do we determine if the model is actually personal data? And some legal scholars have argued that membership inference attacks are actually appropriate and a convenient tool for such privacy audits, right? But let's recall, we've seen that some researchers in literature have noticed that different people can be vulnerable to membership inference attacks to different degrees. And if we use standard approaches to report vulnerability to membership inference attacks, which are usually average-based, right? So average vulnerability, or a similar measure, then we run into the danger of, let's say, privacy washing, in which we will say that the model is private, it's not vulnerable, but really there are some records or there are some groups which are actually vulnerable, right? And here the two settings, they are different, right? So in the first case, where we have some disconnected outliers that have high vulnerability, it is easy to dismiss this as some sort of residual risk, right? They are outliers. This happens. But if we have a whole group that has higher vulnerability than the others, there's a completely different story. And if we're talking about, if we imagine it's some sort of government auditing body, government regulating body that does this analysis, then in a liberal democracy, this body should be accountable to population groups, right? So this situation has to be taken care of seriously. So this is one of the reasons why we should take a look at disparate vulnerability, and in particular, disparate vulnerability across socially salient groups. In the rest of the talk, I'll have different topics. First, I'm gonna talk when are models vulnerable to membership inference attacks in general. So this is not about disparate vulnerability yet. Then when people disparately vulnerable to membership inference attacks. And then finally, I will talk about how can we measure disparate vulnerability. Okay, so let's go and start with when a model is vulnerable to membership inference attacks. And before actually talking about that, I need to introduce some formalizations. So formalize what exactly is a membership inference attack. And I'm going to use a game introduced by Samuel Yam and colleagues. And this game formalizes how a given training algorithm, so not really a model, but a whole training algorithm, let's say model family, is vulnerable on average to membership inference attacks. The game consists of 4 steps. In the first 2 steps, we sample a data set that we denote as S. We sample it from the data generating distribution in a kind of standard for machine learning way, so that it's independently and identically distributed. And in the second step, we train the model on this data set, right? The model we denote as A. The third step is the challenge step. Here, the game throws a random coin that takes values 0, 1. And if the value of the coin is 0, that stands for out of the training data, the game samples a challenge example from outside of the training data, so from the distribution. And if the value of the coin is 1, the game samples the challenge example from within the training data, so from the training data set S. And finally, and this is slightly different from the original game, but the spirit is the same. Finally, the game gives some features to the adversary about this model and this challenge example. So usually this could be loss of the model for this challenge example, or the output of the model for this challenge example, and so on. And then the adversary needs to predict, this has to be an M hat here. The adversary needs to predict whether the value of the coin was 0 or 1, whether this challenge example is coming from the data distribution or from the training data set. And then vulnerability, so we use this high-level concept of vulnerability, but formally we're going to operationalize it as normalized advantage of the adversary over random guessing. Right? So formally we take just the attack accuracy, which ranges from 50% to 100%, and then we want to normalize it into a 0-1 range. And for that, we first subtract the random guessing baseline, which is 50%. And multiply by 2. And in the end, vulnerability ranges from 0 to 1. So it's just normalized accuracy, right, minus the baseline. All right, so now we can talk about when models are vulnerable to membership inference attacks. We know that membership inference vulnerability is tightly connected to generalization and overfitting, which is poor generalization, right? So let's imagine we have two distributions. One distribution on the left here, the red one, is going to be the distribution of models' loss on the training data sets on average, right? And the distribution on the left is the distribution of the model's loss on test data, so outside of the training examples. Right, so the standard generalization, at least one of the standard ways to talk about generalization, is to define it as a difference between the average values of these two distributions. Right, so that's let's say that's going to be classical generalization. It is somewhat easy to see that poor generalization or overfitting is a sufficient condition for models to be vulnerable to membership inference attacks, right? So if we have a high generalization gap between these two distributions, then there exists a very simple adversary that uses some threshold on the loss value. So it takes as input the loss of a challenge example. And if this loss is higher than the threshold, then the adversary says it was outside of the training data set. If the loss is lower than the threshold, the adversary is going to guess that it was in the training data, right? And intuitively, if the average values of these two distributions are different enough, then this simple adversary will have non-trivial advantage, so non-trivial vulnerability, right? But it's also, the problem with this is that overfitting is a sufficient but not a necessary condition to membership inference. And this is also easy to see in this diagram. We could imagine that these distributions of in distribution and out distribution, they are different, but it could happen that they have the same average, right? So according to the classical definition of generalization and overfitting, this training algorithm does not overfit, right? Because the averages are the same, right? But because the distributions are different, there could exist some adversary here that uses this information, because there is some information about what was in and what was out, to have non-trivial advantage, right? So we could have zero overfitting, perfect generalization according to classical definition, but still some membership inference advantage. So what do we need to do to find a necessary condition? And in our paper, we actually show that for this, we need to extend the notion of classical generalization to make it distributional. And we're going to do this in two steps. The first step, instead of looking at the difference between averages of the two distributions, we're going to take some distance between probability distributions. So difference between averages is one example of this distance, but we can take some other distance function that captures more information about the difference between these two distributions. So this is the first step. And observe that here, as before, the distributions are of the losses on training data and outside of the training data. The second step is to look beyond loss. And instead of loss, we can take any other property function of the model and of an example. For example, it could be model's outputs, right? It could be things like model's gradient and other properties. Other properties have been used in the literature. All right, so all in all, we have this notion of distribution generalization that
Did only my stream freeze?
No.
Okay, so it's Bogdan.
looks beyond averages. It looks at the distance between the probability distributions, and hello, can you hear me?
Yeah, now you're back. You were out for a minute. You froze.
Where did I drop? At which point? Sorry about that.
Yeah, no problem. Yeah, at the end, towards the end of this slide, I think.
Okay. Right. So I mentioned that we need to extend the generalization in 2 steps. First, to make it distributional, and the second, to look beyond losses at other possible property functions. So one property function is loss, as in standard generalization, but we could also look at models' outputs or models' gradient and so on. And so all in all, having these 2 steps, we have a notion of distribution generalization. And this notion is very closely related to a concurrent approach to define distribution generalization that has appeared not in context of privacy, but in context of machine learning generalization. So in the paper, we show that a worst case vulnerability, so vulnerability to basically any adversary, is bounded by distributional generalization. The worst case vulnerability equals the distribution generalization gap if we take the distance between probability distributions to be the total variation, which is one of the standard distances between probability distributions. If we were to visualize it, we could imagine that the in distribution has this density and the out distribution has this other density. Have I dropped again? Sorry. No, I'm good.
You're still good.
Paranoid. Sorry.
No, it's all is good.
Okay. And then the distributional generalization gap is just the area between the 2 densities. And by this proposition, worst case vulnerability to membership inference attacks is also the area between these 2 densities. So in other words, what this result shows us is that the concept and say phenomenon of distributional generalization is really the same thing as the phenomenon of vulnerability to membership inference attacks. These are two different ways to talk about the same concept, right? And another way to think about that also is that distributional generalization gives us a necessary and sufficient condition for vulnerability to membership inference attacks, whereas classical generalization is just a sufficient condition. All right. So now we can talk about when are people disparately vulnerable to membership inference attacks. And for that, I'm going to introduce a conditional version of the vulnerability, which is the same as before. It's just the attack accuracy, but it's going to be conditional on the challenge examples that belong to one group Z. Right. So let's look at this, these 2 densities, these 2 probability distributions that I mentioned before, the in and out. We could imagine that they could be pretty similar, right? So they mostly overlap, but maybe on examples that belong to some group, let's call it Z2, they're somehow different. Why don't we zoom in and just look at the distribution, in and out distributions just for this particular group, right? In this case, we could see a very different picture, that these in and out distributions are actually very different. And this corresponds to the case when on average vulnerability is low, but for one subgroup, the vulnerability could be actually high. There's actually a lot of information here for an adversary to distinguish between in and out examples, right? So what we just did is basically just conditioned the 2 distributions. And this corresponds to the notion of subgroup-specific distributional generalization. It's just a conditional version. And to understand how it relates to disparate vulnerability, I need to introduce another concept, that of a subgroup-aware adversary. So the subgroup-aware adversary is just like a normal adversary. It uses some features about the model and examples, such as loss or model output and so on. But in addition to this, to the standard features, it also uses the examples subgroup, right? So that's why it's subgroup-aware. It's a pretty simple proposition that we have in the paper, that actually worst case vulnerability with subgroup-aware adversaries is always equal or higher than vulnerability to the same kind of adversary, but without subgroup information. So subgroup information, on average, always gives an edge to the adversary. So we're going to consider this adversary for now. What we show is that this conditional version of distributional generalization, it equals to the subgroup vulnerability to the subgroup-aware adversary. So it's a bit of a mouthful. And now, because the subgroup-aware adversary intuitively has always higher vulnerability than a normal adversary without subgroup information, the subgroup-specific distribution generalization bounds worst-case subgroup vulnerability. Okay. So this is how subgroup-specific distributional generalization relates to disparate vulnerability. And disparate vulnerability is just the difference between subgroup vulnerabilities of two subgroups. Now, this concludes the theoretical part of this talk. And just to summarize, I mentioned when are models vulnerable to membership inference attacks. And in the paper, we show that worst case vulnerability to membership inference attacks is equal to a notion of distributional generalization. And if poor standard generalization is a sufficient condition for membership inference, poor distributional generalization is a necessary and sufficient condition for a model to be vulnerable to membership inference attacks. Now, when are people disparately vulnerable to membership inference attacks? A subgroup vulnerability is equal to a subgroup conditional version of distributional generalization, and therefore disparate vulnerability, at least to a strong adversary, is bounded by the difference between the degrees of distributional generalization for the two groups in question. All right. So next, I'm going to talk about more practical matters, right? And how can we measure disparate vulnerability in reality? So this should be pretty straightforward, right? We apply some membership inference attack. We evaluate this attack separately on different subgroups of the data, right? And let's say we have a case where we are interested in just two subgroups. Then finally, we report the difference between subgroup vulnerabilities of these two subgroups, right? And that's it. That's our disparate vulnerability protocol, measuring protocol. Unfortunately, this is not as simple as it sounds. Specifically, there are very non-obvious pitfalls when we're doing that that could break the process to some degree. And in this talk, I'm going to talk about one of these pitfalls. And to show this, I'm just going to start with an example. It's going to be slightly silly, but bear with me. Let's imagine that we want to evaluate membership inference attacks against data-independent models. What does this mean? We have a training algorithm that takes as input a training data set, right? It takes it as input and then immediately throws it away, doesn't look at it, and just returns a constant model or random model, doesn't matter, right? You can think of it as a training algorithm that has epsilon differential privacy with epsilon 0. So it cannot memorize, it has not looked at the data even, right? So we should expect kind of 0 vulnerability and 0 subgroup vulnerability and 0 disparate vulnerability. Seems weird, but let's see what happens. Right? So in this experiment, we simulated several settings in which our data set has two subgroups. One subgroup we keep at constant size, at 1,000 example, and another subgroup we vary its size from 25 to 1,000. And then we measure vulnerability on these data sets of data-independent models, right? We measure vulnerability, we measure subgroup vulnerability, and we measure disparity, which is the difference between the vulnerabilities of the two subgroups. So this seems weird, like, what difference does it make if we have two subgroups or not subgroups, the models, the data independent, they're not even looking at the data, right? We should just see zeros all across the board. Okay, so we measure 3 methods, and I'm going to detail in a bit how exactly we apply them. We measure a so-called shadow model attack, and we measure 2 other threshold-based attacks, average loss threshold and optimal loss threshold. I'm going to talk about them in a bit. And what we see is that for average loss threshold attack and for the shadow model attack, we see on average the disparity estimates, therefore the difference between subgroup vulnerabilities, are around 0. But for the optimal loss threshold attack, we see that the disparity estimate can be very high, especially when the subgroup is small. And this diamond here means that according to the statistical test, we have statistically significant difference from 0 at p-value less than, I think, 0.001, right? So what's happening here? The models have not looked at the training data. This is silly, right? Still, we get non-zero vulnerability for one of the groups, right? Therefore, we see high disparity. What's happening here? And to understand what's happening here, we have to understand different approaches to formalizing adversaries' knowledge in membership inference attacks.
Bogdan, before you continue, can I interrupt you very briefly? On the last slide, can you quickly explain the 3 methods, like on a very high level?
Sure.
Because, I mean, people may not be familiar with these terms.
I will explain them in a bit, but just for now, all right. For now, let's just see. These are just 3 different attacks, right?
Okay, sounds good.
So in the literature, we've seen mostly 2 main approaches to formalizing adversaries' knowledge in membership inference attacks. One approach, I'm going to call it shadow model approach, not technically correct, but I'm going to call it for the purpose of this talk. In this approach, we assume that the adversary has some knowledge of the data distribution and the knowledge of the training algorithm. Having these 2 data points, what the adversary usually does is samples data from the data distribution and trains a model on these data sets. And this results in so-called shadow models. They are supposed to mimic the actual target model. And in general, they should be somehow similar to the target model, right? Because they're trained on the same data and they're trained using the same training algorithm. And this is a rather realistic way to formalize membership inference, right? And there's also a different approach that is also pretty common in the literature that I'm going to call a worst case approach. Here, the adversary also has some knowledge of the data distribution, but additionally, here the adversary also has access to some non-trivial information about models' properties on the training data. For example, models' outputs, models' loss on the training data. And 2 examples are the average threshold attack. Here, the adversary gets as background knowledge the average loss on the training data. Seems like a very trivial piece of information, right? But it is still some information about the target's training data. And there are also approaches based on optimal thresholds. In here, the threshold is not just the average loss, but it's carefully chosen to, for example, best separate the losses on the training data and on test data, such as to maximize, for example, attacks accuracy or attacks false positive rate and so on. Right? So here, this is much less trivial amount of information, right? To find this optimal threshold, you actually, as an adversary, have to have the distribution of losses on the training data set. And it's quite a lot of information about the training data. And why we have to be careful about this setting is because, well, what's the goal? What's the high-level goal of membership inference attacks? It is to learn something about the training data. But here we're already starting, the adversary is already starting with some non-trivial amount of information about the training data. And in general, it's okay, right? In general, this is fine. In security, this is normal. It is normal to use worst case adversaries, worst case evaluations. And it's good for practice because it incentivizes caution in deployment, right? Except when it's not. And this is not actually a good thing to do, specifically when we're evaluating disparate vulnerability. So why this can be a problem, right? To answer this, we have to understand why the adversary can distinguish in examples from out examples. Where does this advantage come from? And of course, it comes from the model's memorization. The model is a bit like a parrot. It memorizes something it has seen in training data, and therefore the adversary can tell this difference in behavior on in examples from out examples, right? That's what we want to capture when we're measuring membership inference attack vulnerability, right? But in this case, when the adversary is in this worst case setting, when the adversary has some non-trivial knowledge about the model's behavior on the training data, we have another source of advantage, and this is advantage from finite sampling. And I'm going to give an example how this appears, right? Let's imagine that our data distribution is Bernoulli, 50%. So on average, we should see 50% of zeros and 50% of ones. Very simple data distribution, very simple data sets. And let's sample some small data set for the sake of example, right? Let's say it's a data set of size 10. And we could see that it could happen, right? It could happen that 7 examples are zeros and 3 examples are ones, right? So the distribution generated by the training data set is actually pretty different from the actual data distribution. And now what we're doing in this worst case setting is that we're giving to the adversary the output of some function, which is our target model, but it's some function, right? The output of some function on the training data set and outside. And because the adversary knows that some outputs came from the target model's training data, this function could actually be memorizing. Or maybe it could be completely random, it could be constant. The adversary could still get some advantage just because the data distribution induced by the finite data set is very different from the actual data distribution, right? Whatever function we apply to it, the adversary will be able to tell some difference between in examples and out examples, even if the model has not memorized anything at all, right? And this is actually what we've seen in this experiment that I've showed in the beginning, right? So all in all, with this worst case setting, when the adversary has some access to training data information, we have 2 sources of advantage. First is model memorization, which is a good source of advantage. This is what we want to capture. And second, it's from sampling bias. And this source of advantage is really a bias because it does not correspond to anything that we want to measure. This does not correspond to model memorization. We don't want it. Good news is it depends on the dataset size, and it quickly vanishes as the dataset becomes big. Even when it's, I don't know, 10,000, it already is really insignificant, right? But the problem appears when we start to measure disparate vulnerability. If one of the subgroups is small, then this is equivalent to having a very small dataset size. And in the literature, we've seen subgroups as small as 50, right? And at this scale, the sampling bias does kick in, right? So it does matter, and therefore it gives you an overestimation of subgroup vulnerability for the small subgroup, right? And the problem with that, basically, whenever the subgroup size is different for the 2 subgroups you're comparing, you will always see some disparate vulnerability, some non-zero disparity between the vulnerabilities of the 2 subgroups, just because of the sampling bias, not because of model memorization. Again, this is when we're using this worst case approach. And we propose a simple test that you've actually already seen, the test for Null-Model Bias. And it is just to evaluate the attacks that you have against data-independent models, right? And what we see is that the average loss threshold attack that takes as input, as background knowledge, the average loss on the training dataset, and the shadow model attack, which does not have any information at all about the target model, right? It only uses the shadow models that mimic the target, right? They do not have this bias. They cannot actually use the sampling bias as an advantage. Well, the average loss threshold theoretically could, but in practice it doesn't. In contrast, the optimal loss threshold, in which the threshold was chosen using the distribution of models loss on the training data. This is a lot of information about the training data. Has a lot of bias because it was able to capture this difference between the finite data distribution induced by the dataset and the actual data distribution. And in the end, when the subgroup size is very small, for example, 25 or 50, we see a rather high disparity estimate. Again, this is on data-independent models that have not seen the data set at all, right? So this doesn't make much sense. We don't want that. Well, to avoid that, it is easiest to use attacks that are based on the shadow model approach to modeling adversaries' knowledge, right? In this case, the attack just cannot possibly theoretically capture the sampling bias, and therefore it will be good for estimating disparate vulnerability. Our experiments show that average threshold attack also doesn't seem to be affected by the sampling bias a lot, probably because just the one data point, just the average loss on the trained data is not significant enough to learn a lot about the sampling bias of the trained data set. However, if we use the optimal threshold attack, and the threshold is estimated on the target model's data, you should avoid using that for measuring disparate vulnerability. There are ways to avoid problems with this. There are ways to avoid the overestimation of disparity, but as a rule of thumb, it's best to just completely avoid this approach when measuring disparate vulnerability. All right. I will have to end my talk soon, so I will just briefly mention some other results that we have in the paper. I mentioned there are two pitfalls that we can encounter when measuring disparate vulnerability. I mentioned one, that's the sampling bias. But another pitfall is that when the subgroups are very small, then we actually want to make sure that the disparity estimate that we get is significant. It's not a random fluke. And if in the paper we show how to do that, if we're measuring disparity between two groups, we should use, for example, a t-test. If we're measuring disparity between multiple groups, there's a standard protocol using ANOVA and post-hoc tests with multiplicity correction. And we have the details about that in the paper. Also in the paper, we use these methods that we propose. So basically we use as an attack, we use the average threshold because our experiments have showed it's not biased. And we use the statistical tests to check whether we can actually detect still disparity in the real world data sets. And the answer is yes, we can. We tried it on 2 data sets, adult in Texas, based on Texas hospital discharge data. And we are able to detect disparity, even with using statistical significance tests. This was not done in prior literature. And you can also see the details in the paper. Finally, also in the paper, we talk about how can we prevent disparate vulnerability. First, we show that differential privacy does bound disparity, as we would expect. And another mitigation for disparate vulnerability, kind of intuitively, would be also to employ algorithmic fairness, so ensure that the model's behavior is similar across groups. And indeed, it can remove disparity if the fairness property generalizes, but only for a specific adversarial model, and really it's not at all a good protection in the security sense. The details about this are also in the paper. So this mostly concludes my talk. So let me summarize everything I have talked about so far. I've started with a legal discussion in which I argued why it is important to evaluate disparate vulnerability across specifically demographic subgroups. And this is to avoid privacy washing of machine learning models. I talked about when are models vulnerable to membership inference attacks, and in the paper we show that worst case vulnerability to membership inference attacks is equal to distributional generalization. Poor standard generalization is sufficient for membership inference attacks. This we have known before, and we show that poor distributional generalization is necessary and sufficient condition for vulnerability to membership inference. When people disparately vulnerable to membership inference, when these groups have different degrees of distributional generalization. How should we measure disparate vulnerability? First, we should not use attacks that have non-trivial access to the training data. So we should prefer shadow model-based attacks. We should use statistical procedures to establish if disparate vulnerability is significant or not. And in our evaluation, our experiments, we were able to detect disparate vulnerability using these methods in realistic settings. We also talk about mitigations in the paper, and we show differential privacy bounds disparate vulnerability, and that algorithmic fairness also can bound disparate vulnerability within one threat model. And it's really not a sufficient tool to protect privacy. Okay, so this concludes my talk. Thank you very much for your attention, and I'm happy to take questions.
Cool, thanks a lot, Bogdan. Let me quickly stop the recording.